is going to help you a lot later when you, for example, we discuss different forms of optimizers, like more advanced optimizers, and you see why we do those tricks in them, basically because of this mathematical formulation. So the idea of training is to tune the learnable parameters such that we can make our model somehow fitting our data, right? And then before I start with that, I just want to grasp the notation here. So one point, I want to discuss the random variables, and just wanted to make sure that everybody is on the same page. So we could have a discrete random variable, x. This x is a discrete random variable, for example, a binary variable. When it's a binary random variable, it means that it could be 0 or 1, right? And it's 0 with some probability. It's 1 with some probability, right? So I'm going to say that probability of x being something, x0, for example, is p of x0. If x is binary, then probability of x being 0 or 1 are two different things, right? Everybody's clear? Now, probability values, could they be negative? Could they? No, so they should be positive. What should happen if I add up all the probability values? It's going to add up to 1, right? So you always have this marginalization property, right? So if you have binary variable, the probability of the first 0 plus 1 should be 1, right? If the 0 is happening with chance 0.6, the other one must happen with chance 0.4, right? So this is a discrete random variable. The other random variable is the other type of random variables we could have is a continuous random variable. It means that any real value, for example, right? It's not anymore just binary, right? And then when you have any real value, you cannot anymore define probability value, right? Probability mass is not defined. Think about a Gaussian random variable, right? What is the chance of a Gaussian random variable being 0? What is the chance of that? What is the probability of that? That's 0, right? You can never guarantee that you're going to hit with some frequency exactly the point 0, but you can lie somewhere around it, right? This is why we compute the density function, right? So we usually have the density function. What is density function? Say, if you have density function px, and then you go for one interval, and then you integrate this density function over the interval, then you are eventually computing the probability of your random variable being inside that interval, right? If you integrate the density function of the Gaussian random variable from -1 to 1, then eventually you end up computing the chance that your Gaussian random variable is a number between -1 and 1, right? Everybody's cool? That is density. Can density be negative? Can it be negative? No, it cannot be negative. If it's negative at very tiny point, right? Then when you integrate it exactly around that point, it's going to be negative. So it cannot come a negative value out, right? So density is always positive. Probability is positive. Density must be positive as well. Now, what's going to happen if I integrate the density function from -infinity to +infinity? It's going to add up to 1. Because this is the probability of the Gaussian random variable being something between -infinity and +infinity. That's definitely the case, right? So the probability is 1. So it's again having the same property as the probability mass function, only you replace the summation and probability with the density and integration, right? There is one tiny difference here only, and that is that these p-values here, since they are probability and they are supposed to add up to 1, their own value cannot be more than 1, right? But here density could be more than 1, right? Like a Gaussian, because it's not important the value of density. It should integrate to 1, right? Everybody's cool? Okay, everybody remembers, right? Now, I have a random variable, and I have a distribution for it. So I am not going to specify that I'm talking about density or probability mass function. I don't like it, okay? I have px. If x is continuous random variable, this is density, PDF. If x is a discrete random variable, this is probability function, right? Everybody's cool, right? We just call it distribution. We make it easy for us, okay? Now, the next thing is the joint distribution. So what is a joint distribution? If you have multiple random variables, say x1, x2 till xn, then the joint distribution is the distribution of all of them together, right? If you have two binary variables, the joint distribution is going to be the distribution of all cases of two binary variables, right? So it's going to be 0, 0, this is one case, 0, 1, another case, 1, 0, another case, 1, 1, another case, right? Cool? Now, if you have one image with n different entries in it, then distribution of that image is the joint distribution of all the pixels, right? If you think about your image to be something random, then you can write down a distribution for it, and that distribution is the joint distribution of the all pixels, right? Everybody's cool, right? Good, great. So now, next thing, expectation. You know expectation, right? If I have a binary random variable, say I have a binary random variable, so x, it could be 0 or 1, right? And I need to have a probability distribution for it, so I'm going to write down here 0.3, here 0.7. Can you tell me what is the expectation of this random variable? What is E of x? What is it? You're going to say 0.7. This is the probability times 1. So 70% of the time it's 1. 30% of the time it's 0, right? So it's going to be 0.3 times 0 plus 0.7 times 1. It's going to be 0.7, right? So you can do it for any random variable, right? So any random variable, if it's discrete, then you're going to get every single realization of that. You multiply it with its own probability, and then you add it up, right? This is going to be the expected. If it is a continuous random variable, you are going to replace that summation with integration, right? Everybody's cool? We're fine? Yes? Now, if I replace this x with any function inside the expectation, what's going to happen to that expectation? It's going to be the same expression, just instead of x, you're going to put that function, right? F of x. Everybody's cool? Right? Now that I have this, the only thing that I want to just, the main reason that I said all of these stories is because we need the law of large numbers. Do you know what is the law of large numbers? So, what is it? Say I have n independent realization samples of one random variable. Yeah? The binary case I told you, how I can generate one binary random variable, I can get a coin and just toss it, right? If you flip a coin, it's going to be one binary variable. It's going to be 0, it's going to be head with some chance, tail with some other chance, right? Now I'm going to keep doing this coin flip, for multiple times, right? And I do it independently. Like I just flip this coin, I record the output, then independently again flip the same coin, right? And I keep on doing it, right? Now, I'm going to see multiple independent realization of the same random variable, right? So I have, say, n different, or say I different, I different independent samples by the same distribution. This is what we call it IID samples, right? Independent, identically distributed. All of them are identical in distribution, all of them are binary, and they are just generated independently, right? If you do that, and you look at those x's output, what's going to happen if you average them out arithmetically? What do you see? If the coin that I told you, head and tail, if I call head to be 0, tail to be 1, and if I do it for 100 times, how many times do you expect to see head? How many times do you expect to see 1 if this coin is a fair coin, like 50-50% chance? What do you expect? 50% of the time you're going to see head, 0. 50% of the time you're going to see tail, 1, right? Now if you average them, what do you see? 50 times 1 plus 50 times 0, going to be 50, divided by 100, it's going to be 0.5, right? If you do the same thing, if you compute the expectation of x, you're going to end up with 0.5 as well, right? This is what we call a law of large number. Any random process, if you try it enough number of times and then you average it, then the average that you see is roughly the same thing as you would get by the expectation. And this is why we call it expectation, because we expect, after doing so many experiments, see in average the same thing, right? So this is what we call it a law of large numbers. So if I have multiple independent realizations of x, and then I average them, right? This value is going to be the expectation of x, right? If I do it for so many times when I is very large. If you have a coin, when you do it 100 times, it could be 50-50, it could be 43-57, right? It could be that. But if you do it 1,000 times, then it's going to be closer to 50%, right? It's going to be maybe 493, and then there is 507, right? So it's going to get closer and closer to 50-50, right? And if you do it for infinite number of times, then it's going to be exactly 50-50, right? So this is the law of large number, and this is a very important thing because this is actually going to help us build up some objective which is going to represent our final goal, which is to have the output of our model to be exactly same as the true label. Okay? Everybody is cool on the law of large number? Any question on that? No question? So would it be fine if next session I don't recap that anymore and I just start with the training? Yeah? Okay. But just since it's fresh, the law of large number is fresh, and I have a few extra minutes, just to give you the big picture of what's going to happen. What you can think about your data is that your data, every single sample that you see, every single image that you see, is just one independent image from so many images that you have, right? Now, those independent images, you do know their label, right? Now, what you're going to do, you're going to give that image to your neural network, to your model, and this model is going to process it, give you one label at the output, right? You compare this label to the original label, which was in the data set. You're going to get a loss, right? This guy is one sample loss, right? This means that for that sample image, the loss is this, right? But this loss is not the same for another image, right? What you hope for at the end is that if I consider all the images in the universe, right, then when I process them by my model and I average the loss coming out of that model, right, that one is minimized. But you are not able to compute that because you need to know all the images in the universe, yeah? That is not possible. But what does the law of large number tell you? It does say that if you have just enough number of images and you average the loss for these images, like you have 100 images and average the loss, that loss is not exactly the loss that you want out of the expectation, but this is roughly close to that, right? Fairly close to that. And instead of minimizing that one, just go ahead and minimize this one, right? This point is the reason that we do training in the form that, full batch training. And this is the reason that we can get from full batch training to the mini batch training, which we are going to later discuss, okay? Just wanted to give you the big picture why we need the law of large number. Next session, I'm not going to recap that. I just start directly from training, okay? And we're going to have a very short discussion, and then we get one good example, okay?